Hi, myself as Lakshmanachari, working as Assistant Professor in Department of Cybersecurity, Institute of Aeronautical Engineering, Hyderabad. Today, we will have a question bank discussion on organization of a computer. So, the first question is build the 4-bit arithmetic circuit for arithmetic micro operations. So, the basic component of an arithmetic circuit is the parallel adder. So, by controlling the data inputs to the adder, it is possible to obtain different types of arithmetic operations. So here we are going to build a 4-bit arithmetic circuit. So using this arithmetic circuit, it will generate various arithmetic micro operations that are addition, subtraction, add with carry, subtract with borrow, uh, increment, decrement. So all these various arithmetic operations are generated by using this 4-bit arithmetic operation. Okay, so by controlling the data inputs to the adder, it is possible to obtain different types of the arithmetic operations. So it has four full adders. So we are constructing a 4-bit arithmetic circuit. So it requires four full adder circuits. It requires four full adder circuits. Constitute a 4-bit adder and four multiplexers, choosing different operations. So we require four full adders and four multiplexers for choosing different operations. So based on the selection lines of the multiplexer, we will have a different operations. So there are two 4-bit input A and B and a 4-bit output D. So the four inputs from A go directly to the X inputs of the binary adder. So this binary adder have two inputs. So one of the input is A. It will go directly to the X input of the binary adder, and each of the four inputs from the B is connected to the data inputs of the multiplexer, and the multiplexer's data inputs also receives the complement of the B. The other two data inputs are connected to 0 and 1. So basically we are using a 4 by 1 multiplexer. So the second and third inputs of the multiplexer are connected to the 0 and 1 respectively. So 0 is a fixed voltage value, and one signal can be generated through the inverter, so whose input is 0. So here you can see the a 4-bit arithmetic circuit. So for that we require four full adders. Full adder. These are the four full adders. So these are the full adder 0, full adder 1, full adder 2, full adder 3. So in addition to that, we require four multiplexers. So the size of the multiplexer is a 4 by 1. So the 4 by 1 means it has four inputs and one output. So the inputs are 0, 1, 2, 3. So these are the inputs, and output is this one. And this 4 by 1 multiplexer, it has two selection lines. So selection line S1, S0. So the number of selection lines required, it depends upon the number of inputs. So the number of inputs are 4. So it is in the expression 2 power n. So 4 we can write 2 power 2. So that is equal to 2 power n. So where n is equal to 2. So that means the number of selection lines are required are 2. So the selection lines named as S0 and S1. And one more input, that is a C in, that is an input carry to the first full adder. Okay, so we have a two 4-bit numbers, so that are A and B. So the 4 bits of the A are represented with A0, A1, A2, A3. And similarly, 4 bits of the B register are represented with B0, B1, B2, B3. So these are the 4 bits of the register B. So the bits of A, that means A0, A1, A2, A3 are directly given to the full adder. So this A0 is directly given to the X0. Similarly, A1 is directly given to the X1, A2 also, A3. So all these uh, A number, so that means A0, A1, A2, A3 are directly given to the one of the input of the full adder, and the another input Y0 that is given through the multiplexer. So multiplexer having 4 inputs. So the B0 is given directly to the 0 input of the multiplexer, and the complement of B0 is given to the first input of the multiplexer, and the second input of the multiplexer is given as 0, and the third input we are applying as 1. Okay, so based on this selection lines, one of the input of the multiplexer will be connected to the output. So if suppose if S1 S0 both are 0, the 0 input of the multiplexer, it is connected to the output. Similarly, if 0 1 is there, then the first input will be connected to the output, and if 1 0 is there, the second input will be connected to the output, and if selection lines are 1 1, then the third input will be connected to the output. So in this way, any one of the input will be connected to the output at one point of time. Okay, so based on this so the full adder, it will generate the sum. It will generate two outputs. One is the sum, it is represented with the D, and carry, it is represented with C1. So C1 is the carry from the first full adder. C2 is the carry from the second full adder. Okay, so and so on. So this is a truth table for the this 4-bit full adder. So using this the selection lines S0, S1 and C0 output carry, then mux output, it will generate different outputs. So when the selection lines 0 0 and the if we assume the input carry as 0, then the output of the mux is B. Output of the mux is B. So the full adder output, it gives as A plus B. So this is equivalent to the addition. Then the next combination is a 0 0. So if the selection lines are 0 0 and the C0 is a 1, it will in that case the mux output is a B. Then it gives addition with carry. So A plus B plus 1. In the next case 0 1 0. So that means the selection lines are 0 1. So when the selection lines are 0 1, then the first input, so first input will be connected to the output. So first input means B bar. So B bar is the, it is the input connected to the first input. So B bar will be connected to the output. So that's why the output of the multiplexer will be B bar. So in this when the selection lines are 0 1, it performs A plus B bar. So that means subtraction with bar. And in the next case 0 1, and if we assume the carry is input carry is 1, then it performs a subtraction A minus B. And similarly, if the selection lines are changed to 1 0, so the second input, so second input means to the second input of the multiplexer, we have connected 0 input to the 0 input to the multiplexer. So that's why the output of the multiplexer is 0. So that means it performs the operation A. That means transfer A. Whatever the content is there in the A, that will be transferred to the output. So that's why it is a transfer A. Next 1 0 1. So the output of the multiplexer is a 0. It performs increment operation. It performs increment operation. So it will perform increment operation on the A value. Then 1 1 0. So if 1 1 is there, if the selection lines are 1 1, then the third input of the multiplexer will be connected to the output. So that means to the third input of the multiplexer, we have given 1 as the input. So the output of the multiplexer is 1. So it performs a decrement operation. It performs decrement operation. That means a minus 1. And the last case is a 1 1 1 1. So that means when my selection lines are 1 1 and the we are assuming the input carry is 1. So the output of the multiplexer is 1. So it performs a minus 1 plus 1. Because this plus 1 is we have assumed the input carry as 1. Okay, so a minus 1 plus 1. So plus 1 minus 1 gets cancelled. It will give a as the output. So that means transfer a. So these are the various outputs generated by the a 4-bit arithmetic circuit. So next one is what is the need of subroutine register in a control unit and discuss in detail. So the subroutine register especially we are using to store the return address. So this return address. So especially this is used in when we are calling subroutines. When you are calling subroutines. So what is subroutine? Subroutine is a set of or a sequence of instructions are placed aside in the memory, and that we are calling several times. So that is called subroutine. Subroutine means it is a small program that is placed in a memory aside, and this subroutine is calling from the main program several times whenever we require. So that is called subroutine. So a set of instructions which are used repeatedly in a program can be referred as subroutine. Only one copy of data, one copy of this instruction is stored in the memory. So when a subroutine is required, it can be called many times during the execution of a particular program or the main program. So subroutine it makes programs shorter as well as easier to read and understand because they break programs code into smaller sections. You can test procedures or functions separately rather than having to test the whole program. So this makes the program easier to debug. So especially when we are calling a set of instructions repeatedly, then we are using these subroutine programs. So this is a main program. This is a main program, and this is a subprogram that is called subroutine. So these subroutines are calling from the main program whenever we require. So suppose here at the 78 address we have a instruction call. So we are calling the subroutine. So what is the subroutine? The name of the subroutine. So subroutine. So SUBRUTINA subroutine. So by placing the name of that subroutine, call sub ROU or TINA. So by just calling with the name of the subroutine, then the program control will be transferred from the main program to the subprogram. So here the subroutine is placed at address 1200H. So then the processor will execute all the instructions in the subroutine program. Then always the RET will be the last instruction in the any subroutine program. So whenever this subroutine program is executed, the program control will be returned back to the main program where the call instruction is executed. So that means this call is a 3 byte instruction because it is written like this: call 1200. So call, it is a opcode. 1200 is a address of the operator. It is a address. So it is a totally, it occupies 3 bytes. So that means it is located at 78 instruction. So 78, 79, 80. So these three memory locations are occupied by the this call 1200H. So that means the next instruction is placed at 81H. So that means the 81H is the written address. So whenever the program control is transferred from main program to the subroutine, the return address 81 is stored in the subroutine register, that is called SBR. So that return address is placed in the subroutine. So after going to the subroutine program, it will execute, the CPU will execute all the instructions in the subroutine program, and the last instruction is a return RET. By executing this return, uh, it will retrieve the return address from the subroutine register, so that it can come back to the main program where the call instruction is executed. So the call, after the call instruction, we have a address 81H, so that the program control will be returned back to the 81H, and it will execute the remaining instructions in the main program. In this way, we can call the subprogram many times whenever we require from the main program by simply placing the call instruction. So the subroutines, this makes shorter. So by using this subprogram, that means suppose if you have a factorial program. So factorial program means suppose 5 factorial. That means we need to find 4 into 3 into 2 into 1. So that means that means same operation is performing repeatedly. Suppose if you want to find the 10 factorial, you need to find 10 into 8 into 7 into and so on till 1. So that means the same set of operations we are performing. So instead of writing the multiplication program every time, this program we are writing in as a subprogram, and from the main program we are calling whenever we require. Okay, so that's why the subroutine register, it is used to store the return addresses, especially in the when you are calling the subroutine programs. That is the necessity of the subroutine register. Then illustrate the mapping from micro operation to the micro instruction address. So we are mapping the micro operation of the instruction to the micro instruction address. So the micro instruction address is the 7-bit address, because the control memory size is the 128 128 bytes. So in order to access 128 bytes of memory, we require a 7-bit address. So we are mapping the micro operation. We are mapping the micro operation to the micro instruction address. So if you take a instruction format, so the instruction format is, so the size of the instruction is 16. So 0 to 15. So first 0 to 11 bits, it represents the address, and the remaining 4 bits, that means 12th bit, 13th bit, 14th bit, and 15th bit. So total we have 4 bits to represent the opcode. So opcode means which specifies the type of the operation to be performed, and the address, it is a address of the operand. So a special type of branch execute when a micro instruction specifies a branch to the first word in the control memory where a microprogram routine for the instruction is located. So using this opcode bits, we can specify total 16 operations. 16 operations. That means total we have 4 bits. With the 4 bits, we can specify 16 operations. That means 2 power 4. That is equivalent to 16. So that means with the 4 bits, the initial sequence would be all zeros. Next 0, 0, 0, 1 till all ones. So we are specifying to perform certain operation like add when my opcode bits are all zeros. Similarly, we are specifying to perform subtraction when the opcode bits are 0, 0, 0, 1. So like that, total we can specify 16 operations. Total we can specify 16 operations. So in order to perform this addition operation, we will have a program. We will have a program called micro program. Micro program. So in order to perform this addition, it has to run a micro program. So this micro program, it is located in it is located in the memory, control memory. So the control memory is located in control unit. Okay. So in order to run the micro program, this micro program is stored in this micro program. It is located at a micro instruction address. So that means the micro program can be identified with a micro instruction address. So the status bits for this type of branch are the bits in the operation code part of the instruction. For example, a computer with a simple instruction format has an operation code of 4 bits which can specify up to 16 distinct instructions. So let's see how we can map the opcode bits of the instruction with the micro instruction address. Suppose if the opcode bits are 1011 or the opcode bits of the computer instruction. So these 4 opcode bits we are mapping to the a 7-bit micro instruction address. So in order to map this opcode bits with the micro instruction address, we have to place 1 0 to the left side of the opcode and 2 zeros to the right side of the opcode, so that it will forms as a 7-bit micro instruction address. So that means suppose if 1011, it specifies the operation increment. So that means in order to perform increment operation, we have to run corresponding micro program. So that means this is the address for corresponding increment micro program. So that means the micro program related to the increment is located at this address, micro instruction address. Summarize the common bus system using multiplexers with a neat design. So the common bus system using multiplexer. So common bus system, that means instead of taking individual connections between the registers, we are using a common bus system with using multiplexers. So before going to the in detail, we will have a glance on the 4 by 1 multiplexer. So what is a 4 by 1 multiplexer? 4 by 1 multiplexer is it has 4 inputs and 1 output, and the selection lines are 2. So that means the selection lines depends upon the 2 power n, where n is the number of inputs. So that means total number of inputs are 4. We can write like 2 power 2. So when n is equal to 2, that means the selection lines are 2, S0 and S1. So at any point of time, only one input will be connected to the output. Which input will be connected to the output, that depends upon the selection lines S0 and S1. So this is a truth table. So input I0 and the selection lines are S0, S1. So when my selection lines are 0, 0, the input I0 will be connected to the output. Similarly, when my inputs are 0, 1, the I1 will be connected to the output. When my inputs are, when my selection lines are 1, 0, the I2 will be connected to the output. When my selection lines are 1, 1, I3 will be connected to the output. So in this way, only one of the input will be connected to the output at any point of time. So the following block diagram, it shows a bus system for 4 registers. It is constructed with the help of 4x1 multiplexers, each having 4 data inputs, 1 output and 2 selection inputs. So this is a common bus system using multiplexers. For this, we require 4 multiplexers and 4 registers. Registers A, register B, register C, register D. So using this a 4-line common bus, we can transfer the data from one register to the another register or another device. Okay. So the register A, we have connected, we have made a connections in such a way that the A0, the lower bit of the register A, is connected to the 0 input of the multiplexer 0. Similarly, the first bit of the register A, it is connected to the A1 of the, it is connected to the 0 input of the multiplexer 1. And second bit of the register A, A2, is connected to the 0th input of the multiplexer 2. Similarly, A3 is connected to the 0th input of the multiplexer 3. So, in order to transfer the contents of register A to the another device, so I need to select the selection lines as 0, 0. So when I choose the selection lines as 0, 0, so this the 0 inputs of the all the multiplexers will be connected to the output. So here zeros input will be connected to the output. So that means so here it will, the output of the mux 0 is A0 and the output of the mux 1 is A1, output of the mux 2 is A2 and output of the mux 3 is A3. So that means the contents of the register A is transferred to the output to some other device using a 4-line common bus. And if you want to transfer the contents of B to the another device or another register, then we have to choose the selection lines as 0, 1. So that means S0 as 1, S0 as 1 and S1 as 0. Similarly, if you want to transfer the register D data, then we have to choose the selection lines as 1, 1, so that the register D data will be transferred to the other device or other register through this 4-line common bus. So this is a common bus system using the multiplexer. So when the selection lines are 0, 0, register A is selected. When selection lines are 0, 1, B is selected. And when selection lines are 1, 0, C register is selected. And then finally, when the both selection lines are 1, 1, then the register D is selected. And define micro operation and illustrate arithmetic micro operations with examples. So what is micro operation? Micro operations are the operations that are performed on the data stored in registers. That is called micro operation. So this the arithmetic micro operations. So the arithmetic micro operations are deal with the operations performed on numeric data stored in registers. So in general, we are performing all these arithmetic operations on the data or numbers stored on the registers. So we have some arithmetic operations that are addition, subtraction, increment, decrement, and shift. So these are the basic arithmetic micro operations. So in addition to these basic arithmetic micro operations, we can also have some other arithmetic micro operations that are addition with carry, subtraction with borrow, transfer, or load. So these are the addition, subtraction, complement, one's complement, two's complement, subtraction using subtraction using the two's complement, increment, decrement. So these are all the various arithmetic operations. So here the contents of R1 is added with R2. It is a addition. Here the contents of R2 is a subtracting from the R1. Performing one's complement, performing two's complement. So two's complement is nothing but performing one's complement. Then we are adding 1 to the one's complement. It gives two's complement. And coming to explain a 4-bit binary adder along with a neat sketch. So the digital circuit that performs arithmetic sum of 2 bits and its previous carry is called full adder. Okay, so the full adder is used to add to find the sum of the two bits. Okay, and its previous carry. So that means the full adder, it has 3 inputs and 2 outputs. So 2 outputs are sum and carry. So the digital circuit that generates the arithmetic sum of two binary numbers of any length is called binary adder. So using this binary adder, we can find the sum of any two numbers of any length. So this is a 4-bit binary adder. It is a this is a 4-bit binary adder. That means we have a two numbers A, B, and their bits are represented with A0, A1, A2, A3. So these are the 4 bits of the A. And similarly, we have 4 bits of B, B0, B1, B2, B3. So in order to perform addition between these lower bits, we have one full adder. Next, another full adder. So like that, total we have 4 full adders: full adder 0, full adder 1, full adder 2, full adder 3. So before going to the know the operation of the 4-bit binary adder, we will see the circuit diagram, logic diagram, and the truth table for the full adder, so that we will have some idea. So this is a n-bit binary adder. N-bit binary adder. The n-bit binary adder, it requires n full adders. So here we are discussing a 4-bit binary adder. Binary adder. So it requires 4 full adders. So this is a circuit diagram of the logic diagram of the one full adder. Okay. So this full adder, it has 3 inputs: input A, input B, and input carry. And it produces 2 outputs. One as a sum and another one is a carry. So the sum expression is A exclusive OR operation with B exclusive OR with C. Similarly, the carry out expression is AB plus BC plus AC. So it gives the carry. So inputs are A, B, C, and outputs sum, carry. So since we have 3 inputs, we can have 2 power 3 combinations. That means 8. So this is 0, 1, 2, 3, 4, 5, 6, 7. So total we have 8 different combinations. So when all my inputs are 0, 0, 0, what will be the my sum? So sum is A XOR with B XOR with C. So 0 XOR with 0, 0. So 0 XOR with 0, 0. So sum is 0. And carry is also 0. Similarly, if 0, 0, 1, what about my sum? Sum is 1 and carry is 0. So like that we will get all sums and carries. And coming to here, so for analysis purpose I'm taking two values. A value is the 5 and B value is the 4. So 5 means in binary I can represent 0 1 0 1. So that means this is A0, A1, A2, A3. Similarly, B value is a 4. 4 I can represent in binary as 0 1 0 0. So this is a B0, B1, B2, B3. So I'm performing the addition. So if I add 5 plus 4, it has to give 9 as a sum. So 0, 1 plus 0, 1, 0 plus 0, 0, 1 plus 0, 0 with carry 1. So, okay. So it gives 9 as the sum. So let's see. So the initial carry is the 0 and I am representing all corresponding bits in the as inputs. So A0 is the 1, A1 is 0, A2 1, A3 0. Similarly, B inputs 0, 0, 1, 0. So since my for the first full adder, so this is a first 0 full adder 1, 2, 3. So for the full adder 0, the inputs are 0, 1, 0. So the sum is the 0 and the carry is the 0. And for the second one, for the full adder 1, all inputs are zeros. So my sum and carry also 0. So sum is 0, carry is 0. And for the full adder 2, the inputs are 1, 1, 0. So the sum is 0, carry is 1. For the full adder 3, inputs are 0, 0, 1. So the sum is 1 and the carry is a 0. So the sum expression is the A naught XOR B naught XOR C naught. Similarly, the carry expression is a AB A naught B naught plus B naught C naught plus A naught C naught. So like that we will get all the corresponding sums and carries. So finally for the result we need to get all these sum bits. So sum bits are 1 0 0 0. So it's this is in binary. So its corresponding value in decimal is it is 1. It is 1 here. So the corresponding number in decimal is 9. So in this way, a 4-bit binary adder it adds any two numbers of any length. Okay, so in this lecture we have discussed question bank problems. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.